Alright, so we started chapter 6 on Monday with systems of equations, and it was or Wednesday, whatever. And it was a big section. We learned how to graph systems of equations. We learned how to solve them using the substitution method. We learned how to solve them using the addition method. We learned that there's consistent, inconsistent, and dependent systems, and all sorts of stuff. And I told you that when we do systems of equations, in this class, we were only going to be concerned with systems of equations where we had two equations, two variables. And that is true in terms of solving them using the substitution and addition method. However, now in 6.3, we're going to learn about matrices, and we're going to do systems of equations with three variables, three unknowns with matrices. So, we are going to talk about systems of equations with x, y, and z today, but we are not going to do the substitution method or the addition method or any of those. We're going to learn how these play out using a matrix. And a matrix is a rectangular array of numbers. Matrices are always indicated with these big squared off brackets, and then you list your numbers inside, or you list your elements inside. An augmented matrix has a vertical bar which separates coefficients from constants. This is where we're going to use matrices to write systems of equations, in essence. You can have a matrix that's any size. A matrix could be one element. A matrix could have 1,000 elements in it. Because we are going to be dealing with matrices that deal with three variables, three unknowns, our matrices are mostly going to look like this first one, where it's a three, or a row by column, so 3 by 4 matrix. One of the first steps or style of problem you're actually going to encounter is translating a system of equations into an augmented matrix. So this system of equations that's given has three equations, and most of the equations have three variables. We have an x, a y, and a z in all of them except for that top equation. That top equation is missing the x term. So just like when we did long division, we have to put a placeholder in for the missing variable. Okay? So over here, I wrote the exact same system, but I wrote 0x. We have to have a placeholder. And in general, when we have our matrices, we have our system of equations, we want them in ax plus by, and in this case, plus cz equals d. AKA, you want them to be all lined up like we did for the addition method. That's what you want to do. Line up your x's, line up your y's, line up your z's, line up your equals, and put everything else, put your constant on the right-hand side. That way, when we start making matrices, what's going to happen is you take your coefficients for your different variables and you write them inside of your matrix. So I had 0 x's, 2 y's, and -1 z's. So I have 0 to -1. And then I have a big vertical bar, and I put my answer, or my constant, on the other side of it. So this first row actually represents this first equation, where I have my x, my y, my z term, and my constant. And then I do the same thing for my second equation, where I have my x, my y, my z, and my constant. So that when I'm done putting this system of equations into a matrix, what ends up happening is this first column tells me my x values, like the coefficients in front of my x's. The middle column tells me the coefficient in front of my y's. The last column tells me the coefficient in front of my z's. And then everything to the right of my bar is the answers, or the constants. So we should be able to go from systems of equations into the matrix, But then also, if you're given a matrix like this, you should be able to go backwards and write a system of equations from it, knowing that this is your x's, your y's, your z's, and your constants. Does that make sense, how we go from one format to another? The big key thing is making sure that your columns consist of the same variable, and that if you're missing a variable in one of your problems, in one of your equations, you're putting in that 0 placeholder. Every single spot in your matrix has to have a number. It has to be filled. I'm going to slide up, because this is kind of the big part of our notes. Once we have our matrix, we have 3 different matrix row operations. Your matrices consist of rows, which run horizontally, and columns, which run vertically. Think about like columns, like Roman Colosseums and columns, they hold up the building, so they run vertically. And you walk down a row like an aisle, so those run horizontally. So the first row operation that you're allowed to do is you're allowed to interchange 2 rows. You can move them around. Now, that's not moving my numbers around inside of the row itself. It's literally taking like row 1 and switching it with row 2. I can do that. And the shorthand is written on the left, where I have a capital R, and then that lowercase I or J tells me the number of the row that I would do. So if I'm interchanging row 1 with row 2, it would say R1 and then this little arrow symbol R2, telling me I'm going to flip-flop those. So I can move 2 rows around. I can also multiply the elements of a row by a non-zero number. I can multiply an entire row by a constant. Think about when we were solving systems of equations in 6.1, we were allowed to multiply one or both of our equations by a constant so that when we added them together, something would fall out. That's basically what we're doing here. We're multiplying a row by a constant. It just can't be 0, which you really wouldn't do anyways, like in a regular equation either. The last one, the last row operation we're allowed to do is where we can multiply a row by a constant and then add that to another row. Elements in a row can be multiplied by a non-zero number, basically step like operation number 2, and then added to the corresponding elements in another row. The key here for this third one is that it's the RJ row, the one that's not multiplied by a constant, that's getting replaced. This one is getting replaced. The other one does not get replaced or changed at all. We're going to multiply that row by a constant and add it to another row. And we're going to get examples of all this and see how all this pans out and plays out. The little star note states that 2 matrices are row equivalent if one can be achieved from another by a series of row operations. So if we can do these 3 different row operations and we can get to a totally different matrix, we can say they're equivalent or equal to each other because we did just these 3 row operations that are sound and good, and we're able to do that. And row echelon form is actually going to be your goal for a lot of this. This row echelon form is the main goal that's listed down here at the bottom. And what it is if we're talking about like a 3x4 matrix like this, we have a diagonal of 1s running from the top left to the bottom right-hand corner with zeros underneath, just like this. This is row echelon form. If we can get our matrix to be in row echelon form, we can actually solve our system of equations. Because that's what we're using matrices for. We're using the matrix as a tool to help us solve these 3 equations, 3 unknowns systems of equations. Over. Okay. So the first thing we're going to do is we're going to look at a matrix. It's already put together for us, this augmented matrix, and we're just going to do each of the different row operations so we can kind of see how this feels. So the first row operation is interchanging 2 rows. We're going to interchange row 1 with row 2. Bless you. If I'm interchanging row 1 with row 2, am I doing anything with row 3? No. So that's usually where I start. I start with the row that I'm not touching, and I go ahead and write it down so I don't worry about it. I don't forget about it. I don't accidentally try to play with it. It's down. I'm done. I don't have to worry about it. So now if I'm interchanging row 1 and row 2, I'm literally flipping them. I'm taking everything in row 2, and I'm going to write it in row 1. So that becomes 1, 2, -3, and 5. And I'm taking everything in row 1, and I'm writing it in row 2. 3, 18, -12, and 21. I don't change the order. I don't add them together. I don't do anything. I just change their rows. That's it. That's how that first row operation works. Now, for all these other row operations that we're going to do, we're going to reference the start. We're not going to reference the one we just did. We're going to go all the way to the start, okay? So, the second row operation is where we are taking the row indicated and multiplying it by a constant. It can be a fraction. It can be a whole number. It just can't be 0. So, we are going to take, which I'm going to scroll up so you can see it here. This is the starter. We're going to take row 1 and multiply it by a third. Now that means I'm not touching row 2 or row 3. So again, I generally would write row 2 and row 3 first. You don't have to. That's just kind of the habit I get into. That way I know exactly which ones I'm messing with. So row 2 I didn't play with. Row 3 I'm not playing with. So then the only thing I have to fill in is my top row. Row 1, I'm taking each element times 1/3. So 1/3 times 3 will give me what? 1. 1/3 times 18. How about 1/6? Yeah, basically we're taking each of these numbers divided by 3. That's what we're doing. So -12 divided by 3. And 21 divided by 3. 7. The last row operation is obviously the most complicated because we're doing more things. We are multiplying a row by a constant and adding it to another row. And remember, the key thing here is we are replacing the one we're not multiplying by. So in this case, if we're taking 2 times row 2 and adding that to row 3, we are replacing row 3. We don't do anything with row 2. Row 1 and row 2 in this case will stay exactly as they are in the beginning. Nothing changes with them. Okay? This is the one that confuses students. Nothing changes in row 1 and row 2. I'm going to make my matrix a little bit bigger this time. So row 1 was 3, 18, negative 12, and 21. Row 2 was 1, 2, negative 3, and 5. And I'm actually going to reference, I'm scrolling that down a little bit. This was row 3 from the previous problem, so I'm going to have it up there so that we can see it, just because it's hard to get everything on the screen at the same time. So what we're going to do is we're going to take 2 times row 2 and add it to row 3. So I'm going to write out the long version first, and as you get used to this, you won't have to write it out, okay? So I'm taking 2 times row 2. Well, what's in row 2 at this spot? 1. And I'm adding that to what's in row 3 at this spot, which is negative 2. Now that's just for this spot. I do that for every spot in row 3. So I'm taking 2 times row 2, which will be 2. I'm adding to that what's in the corresponding spot in row 3, which is negative 3. 2 times row 2 plus the corresponding spot in row 3. 2 times row 2, add to that the corresponding spot in row 3. The only row that changes is row 3. Yes, we're using the information from row 2 to change row 3, but row 2 does not change. So we get 3, 1, positive 2 minus 2 will give me 0. 4 minus 3 will give me 1. Negative 6 plus 4 will give me a negative 2. 10 minus 6 will give me 4. Questions? Our row operations allow us to change rows, to multiply a row by a constant, and then to multiply a row by a constant and add that to a different row. Now, the whole reason we learn these different row operations is because we are going to solve our system of equations, our 3 equations, 3 unknowns, simply by doing these 3 different row operations. And our goal is going to be to go from our matrix that they give us, or our system that they give us, and get to that row echelon form. That form where we have the 1s diagonally with the 0s underneath, that's what we're going to try and get to. And there was a famous mathematician named Gauss who came up with a way to do this. His name is Gauss. And so his system for doing this is known as Gauss elimination or Gaussian elimination. It allows us to solve systems of equations regardless of size simply by making a matrix and using the row operations to get a row equivalent matrix to row echelon form. So step 1 will be to write your system of equations as an augmented matrix. Step 2 will be to use those 3 different row operations that we just played around with to change our system of equations into row echelon form. And once we are in row echelon form, we will write it as a system of equations again, and we'll be able to do some back substituting to solve for our remaining variables. One of the slight disservices that I think this class does is that we don't teach you how to solve systems of equations with 3 equations, 3 variables. That's what we skip. And I think because we skip that section, you don't fully appreciate what you're about to get ready to do. Because solving a system of equations with 3 equations, 3 unknowns, we use substitution, and there's a whole lot going on. Like you get 6 or 7 different equations that you're playing around with all at once. Maybe you did this in high school and probably an Algebra 2 course. But it gets to be a lot. And there's nothing wrong with it. It's kind of fun. But there's a lot that goes on. This Gaussian elimination allows us to really keep things nice and neat, and it simplifies it quite a bit. So, if you want to fully appreciate it, you can go back and look at 6.2, which is what we skipped, and see how this all plays out. Or during finals review, I can show you how this plays out. Not that that's on the final, but it's still nice to see. So we're going to use Gaussian elimination to solve this system of equations. 2x minus y plus 4z equals negative 3, x minus 2z minus 10z equals negative 6, and 3x. Notice there's not a y. I left that space intentional so that it really stands out that there's not a y term in that bottom equation. And it hopefully reminds you that we will have to put in a placeholder when we make our augmented matrix. Are we okay if I take at least the elimination part, this top 4 steps off? Okay, because I have this part for you guys. All right. Step 1 of Gauss says we need to write an augmented matrix for our system. So you can go about this 2 different ways. You can write it line by line, which is equation by equation, or you can do column by column. Whatever works for you. I think I'm going to do column by column, so the lineup. Remembering that the column 1 is the coefficients of your x's. So I have 2, 1, 3. Column 2 will be the coefficient of your y's. Negative 1, negative 2. And then what do I do for the bottom equation? 0. I got to put that placeholder in. And then coefficient of my z's will be 4, negative 10, and 4. Put my vertical bar and do negative 3, negative 6, and 7. Right here is also where I'm going to go ahead and remind you of what our goal is. We want row echelon form. 1, 0, 0, A, 1, 0, B, D, 1, C, E, F. This is our goal. And we're going to get there by doing our row operations to our matrix. So the way we're going to do this is we are going to use our row operations to manipulate our columns. Okay, that sounds a little counterintuitive, but we're going to do our row operations and we're going to go column by column. Okay, so the very first thing that we are going to do is we want to start to get a 1 in the upper left-hand column. So this very first step almost always will be a row interchange. That should be, if you can do a row interchange to get a 1 in that top left corner, let's do that. So the way that we do that is we look down column 1 and say, is there a 1 there? Yeah, there is, in row 2. So I can do row 1 and interchange that with row 2, and that's going to get me a 1 in that top left-hand corner, which is what I want. So I'm switching row 1 and row 2 around. And when I'm doing these problems, whether it's for a lecture like this or in my own work, I always write out to the side what I'm doing. So I'm not confused later on what steps I took. I always write out those little shorthands over to the side. Okay, so we got the 1 in the upper left-hand corner. Now, we have to get these to be zeros. When we need to get something to be a 0, you are always going to end up using step number 3, where you're multiplying a row by a constant and adding it to the other row. So the question becomes, if I'm looking at this spot right here in row 2, and I need 2 to go to 0, what do I add to it? What do I add to 2 to get to 0? Negative 2. So can I multiply one of these other rows and add it to that? Like, can I get negative 2 from one of these other rows? The key is going to be starting with row 1, because row 1 has a 1 there. And I can multiply row 1 by negative 2. So I can take negative 2 times row 1 and add that to row 2. If I do that, if I take negative 2 times 1 and add that here, I'm going to get a 0, aren't I? And that's going to give me what I need. So row 1 stays. Row 3 stays. As you get more comfortable, you'll be able to do more than one thing at a time, and I'll show you that in a minute. But for right now, don't feel like you have to rush it. Take it step by step by step. So I'm not going to write out the long form, but I'm taking negative 2 times negative 2, or excuse me, negative 2 times 1, which is negative 2, and adding to that to 2, which will give me 0. Negative 2 times negative 2 will give me a positive 4. 4 plus negative 1 will give me positive 3. Negative 2 times negative 10 will give me a positive 20. Add to that a positive 4, which will give me 24. Negative 2 times negative 6 will give me a positive 12. Minus 3 will give me 9. So now, if I'm looking at column 1, the only thing that needs to happen is that bottom 3 needs to get to a 0. What am I going to do to make that into a 0? Thinking about how I just got a 0 in row 2. That's exactly right. That's exactly right. You're going to take negative 3 times row 1, because that's where we have our 1, we're going to add to that row 3, because when we do that, we'll take negative 3 plus 3, which will get us to 0. So in this one, our top 2 rows are not going to change. Six, 30, 18, Now, as you get more comfortable with doing these row operations like this, if you'll notice the last 2 row operations we did, both dealt with row 1, but we didn't change row 1 at all. All we changed was row 2 and row 3. So at some point, you may get to where you are comfortable, and you can do 2 of them at the same time. Because it didn't have any effect on row 1. I was using row 1 to achieve my new row 2 and my new row 3, so I did both of them on the same step. So that can happen as you get more comfortable. Okay, so our first column now is correct. So after this very first switcheroo, you almost never will use that one again, because it will mess up everything else from here on out. So that's why generally we use this one first if we need to use it at all, and then we use the other 2 to move on. Because our first column now is good. So if we're looking at the row echelon form, the next thing we have to get in column 2 is a 1 in that middle spot. Just like here we started getting the 1, we got the 1 in the upper left corner, now we need to get a 1 right here. If you need to get a 1, you're always going to use row operation number 2, where you multiply by a constant. Because what can we multiply 3 by to get a 1? Exactly right. So what we're going to do is we're going to take 1/3 times row 2. Some of you might be thinking, well, why don't we just add to that like a -3 from one of the other rows? Because when we start adding from other rows, what happens is it'll mess up our first column. Because when you start adding numbers to 0, they're no longer 0, and so it becomes a problem. But if you multiply 0 by a number, it doesn't change it. So that'd be 0, 1, 8, and 3. Now that we've got our 1 in the right spot, we need that 6 to go to 0. So thinking about how we achieved our other zeros in column 1, what do you think we're going to do to achieve a 0 there in column 2?
-6 times row 2 plus row 3.
That's exactly right. You will always go to the row that's basically right above it. Because let's pretend, just for a second, that row 1 was 1, 1. And you're like, oh, well, I could take -6 times row 1 and add it. But then that would affect column 1. So you're always going to go to the row that's right above it. So I'm going to take -6 times row 2 and add to that row 3. So my first 2 rows don't change. Negative 6 times 0 plus 0 is 0. Negative 6 times 1, 0. Negative 48 plus 34 is a negative 14. Negative 18 plus 25 will give me a positive 7. Oh, we're really close to our our row echelon form. Remember, our goal is to get a diagonal of 1s with zeros underneath. We've got our zeros. We need this negative 14 to be a 1. That's need 1. And if we need a 1, that's when we use operation number 2. So what am I going to do? Thinking about how I got this one to turn into a 1. What am I going to do to the negative 14 to turn it into a 1? Yep. I'm going to multiply that whole third row by negative 1/14, which sounds really crummy, but if you look at the numbers we're dealing with, they're not too bad. So the first two rows don't change. Eight, negative 6, 3, 0, 0, 1, negative 1 half. Okay, you're like, great, we got what we wanted. Now what did we get? We actually have started solving our system. Because if you remember, this first column was our x coefficients, our y coefficients, and our z coefficients, and then our constants. So now that I've gotten to row echelon form, I'm going to write a system of equations based on this information. So that top row becomes an equation where I have 1x minus 2y minus 10z equals a negative 6. Then I move down to my second equation where I have a y plus 8z equals 3. And then my bottom row, I have a z equals a negative 1/2. So here's my new system. And because we have spent the time getting it to row echelon, we will always know what z is. Z is negative 1/2. So we can back substitute that negative 1/2 up one row or one equation and figure out what y is. Because y plus 8 times z, well, z is negative 1/2 equals 3. So y plus, or I guess that'd be minus 4 equals 3. Y equals 7. And if y equals 7 and z equals negative 1/2, we can plug both of those things into the top equation to figure out what x is. Because for x, we have x, not on screen, minus 2 times y, well, y was 7, minus 10 times z, z was negative 1/2, equals negative 6. So x minus 14 plus 5 is negative 6. X minus 9 equals negative 6. X equals 3. And we have an ordered triple of 3, 7, negative 1/2. It's not an ordered pair anymore because we have 3 numbers. We call it an ordered triple. Okay, so we're going to start with Gauss-Jordan. This is the same system that we did Gauss elimination. So I'm going to write our last matrix under here so that we know where we're starting from. This is our echelon form matrix that we were able to get to. When we did Gaussian elimination, we got to this stage, and then we switched from matrices over into our system of equations again, and we did our back substitution, and it worked great. We were able to solve it, not a big deal. But now with Gauss-Jordan, we want to get to the reduced row echelon form. So that means we want to get to 1, 0, 0, 0, 1, 0, 0, 0, 1, A, B, C. We want to get to this, because if we get to this reduced row echelon form where the only thing we have is a diagonal of 1s, then we don't have to do any back substituting at all, because Z will be C, and Y will be B, and X will be A, and we're all done and good. So if you remember from Gauss, we did our row operations, but we went column by column. Remember that? We started with column 1, and we got a 1 here, and then we focused on getting our zeros. Then we focused on our 1, then we focused on our 0, and that's how we did this. So what we're going to do is we're first going to focus on getting this to be a 0. That needs to be a 0. So I know it's been since the last one. When we were getting zeros, does anybody remember which row operation we were using? Row operation 1 is where we just interchange 2 rows. Row operation 2 is where we multiply by a constant that's not equal to 0. Row operation 3 is where we multiply a different row by a constant and then add it to a row. Yeah, we did option 3. So what do we need to add to -2 to get to 0? 2. So can I multiply one of these rows by 2 so that when I add it to there, it's going to go away? Yeah, row 2. And look, because this is a 0, if I multiply this by 2, it's not going to change that one at all. Do you see that? So yeah, we want to take row 2. So I'm going to take 2 times row 2, and I'm going to add that to row 1. Remembering that this second one, row 1, is the one that gets changed. So I'm not changing row 2, I'm not changing row 3. I'm only changing row 1. So I usually write down everything I'm not changing first. Then I'm taking 2 times row 2, which in this case is 0, and adding that to row 1. So this is 1. 2 times row 2, 2 times 1 is 2, add that to -2, I get 0. 2 times row 2 is 16. I add that to row 1, give me a positive 6. 2 times row 2, give me 6, add that to row 1, I get 0. But now our first 2 columns are all set up for reduced row echelon form. Because we have our diagonal of 1s and we have 0s everywhere else in our first 2 columns. So if I look at my last column, at least to the left of my vertical bar, those need to be 0. That's what I'm missing. So how do I get 6 to go to 0? What do I add to 6 to go to 0? -6. Okay, so can I multiply? That's row 1. So can I multiply one of the other rows by -6? and add it to row 1?
Yes, the last one.
Yeah, that last one. Look at that last one plays really nice because the zeros mean we won't mess up column 1 or column 2 at all. And then this 1 will help us just get rid of this. So this is one where I am going to show you two things at once. Okay, don't freak out. I can take negative 6 times row 3 and add that to row 1 to get rid of my 6, right? How am I going to get rid of my 8? Multiply row 3 by negative 8. We can do both of these at the exact same time because row 1 and row 2 are not interacting with each other at all. The only thing that's happening is we're taking row 3 times multiple different things and then adding them to the other ones. So row 3 is the only one that's not going to change. And if it makes you uncomfortable to do two of them at once, just do the negative 6 times row 3 plus R1 and then rewrite the matrix and do the second one. It just saves a lot of paper space the more comfortable you get with doing more than one of these at a time. So the nice thing is the first two columns don't change because we would be adding 0 to them. And then the other column becomes 0, 0. That's the whole purpose behind what we're doing. So really the only thing we're concentrating on is changing our answers on the right-hand side. Where I'm taking negative 8 times negative a half, which gives me a positive 4, and I'm going to add that to row 2, which will give me 7. Negative 6 times negative a half will give me positive 3, and I'm adding that to row 1, which there wasn't anything there. This last category is my ordered triple. Because what I have is I have z equals negative 1/2, y equals 7, x equals 3. So that my ordered triple is 3, 7, negative 1/2, which is what we found when we did Gauss and we did back substitution. Because when we did Gauss, we got down to z equals negative 1/2. We back substituted that up so that we found y is 7, and we back substituted both of those up and found that x was 3. We got the exact same ordered pair, which you can't see, same ordered triple, excuse me, of 3, 7, negative 1/2, using Gauss over here in green and using Gauss-Jordan over here in blue and red. Gauss-Jordan, there's no back substituting. Once you get the reduced row echelon form with a diagonal of 1s, you are good to go. Okay. We're going to do another one. Here's your new system. This one is asking for Gauss-Jordan. So you're going to get all the way to the reduced row echelon form. And we have to start all the way at the beginning because we didn't start with Gauss and, solve it and then continue on with Jordan. So the blue is our goal. That is our reduced row echelon form. So what is step 1? What do we got to do? Who remembers? That's right, we got to write an augmented matrix for our system. What that means is if by some chance it wasn't already written in X, Y, Z equals number format, you'd want to do that first. but I don't think it's ever mean enough that it's not going to do that. So once it's written like that, you're going to have a column of your x coefficients, a column of your y coefficients, a column of your z coefficients. Then you put the vertical bar through your equals, and then you have your column of answers. So my x coefficients are 1, 2, 3. My y coefficients are -1, -3, -4. My z's are -2, 6, and 4. Then we do our vertical bar, 2, 5, and 12. And there's our augmented matrix for this system. And since we are trying to get a diagonal of 1s, what you're going to do is you will get to the echelon form first, where you'll have your diagonal of 1s with your zeros underneath, and then you will focus on the zeros on top. Okay, so we do go about it in that system. If we look, we actually already have a 1 in that upper left-hand corner, so we don't have to do any row switching. So that's nice. What we need is we need these to be zeros. And think about how we just got zeros in the previous problem. How are we going to get 2 to be 0?
Multiply row 2 by multiply row 1 by -2. Add it to row 2.
Exactly right. We're going to multiply row 1 by -2 and add that to row 2. So row 1 is going to stay the same. We're going to take -2 times row 1 and add that to row 2. Anybody want to venture a guess on what we're going to do to turn that 3 into a 0?
The same thing except for -3?
Yeah, -3 times row 1, and we're going to add that to row 3. Give me 0, 0. -2, +2, -1. 3, -1. We get a bunch of -1s. Yep. 4, 10, 6, 10. -4, 1, 6, 6. So our first column then is done. So what do we need to focus on next? Yep. So we're going to focus on the 0 on top, the 0 on bottom, or the 1 in the middle. We're going to start with our 1s. We focus with the 1s first, and then do the zeros, and then we'll do the zeros on top. So what we need is we need this to be a positive 1. Need 1. So how do I get that to be a positive 1? One of our 3 row operations was the way that we got positive 1 every time. We're going to multiply the entire second row by a -1. That's our second type of row operation. My matrix is all wonky, like tilted. Sorry. So I'm going to take -1 times R2. Which will give me a positive 1, a -10, and a -1. How am I going to get a 0 down there where that -1 is? I'm just going to add the second row to the third row. I don't actually have to multiply by a constant like I did up here because they're already ready to go ahead and get to 0. And that's totally okay. So I'm going to add row 2 to row 3. So row 1 and row 2 are not going to change. And I'm taking row 2 and adding that to row 3. So remember, the second row that's listed is always the one that gets replaced. Uh-oh. What do you notice? Okay, but when we think about the fact that these represent equations, what do we have on that bottom row? That's right. This bottom row tells me 0 equals 5. Is that true? No. So what does this mean? No solution. What kind of system is this? Yeah. This is an inconsistent system made up of parallel lines. So if everything falls away and you get a false statement, the fact that we're dealing with matrices now instead of an actual system, like in system formatting, doesn't change anything. It's still an inconsistent system. Whether we get that graphically or we get it using the addition method, the substitution method, or now with matrices, it doesn't change anything. We still have those 3 types of systems. So from 6.1, here's your little refresher. 6.1, you have consistent systems. That's where they are exactly one solution. And those are the ones where you're getting a system, or you're getting an ordered pair, an ordered triple, depending on how many variables you have at play. The inconsistent system is what we just had, where we got a false statement. They're never going to cross, so there is no solution. And then I guess that's going to kind of, spoiler alert, tell you what our next one's going to do a little bit, so we can see what that looks like with matrices, where the lines lay right on top of each other. So this is from 6.1. We've seen this before. But something I want to point out is I want to point out that we actually knew a little earlier on that there was an issue with this one. And actually it's right here. Right here, actually. So by this time we got to our second matrix, we could have identified that there was a problem. Because look at the left-hand side. We have 0, 0, -1, -1, 10, 10. They're exactly the same. These 2 rows are. But on the right-hand side, we don't have the same thing, which means we are saying 1 equals 6 at this point, which is false. So at this stage even, we could have said this is an inconsistent system, and we could have stopped. We kept going, because I really want it to be noticeable what happens. But really at this point, if we have 2 rows that are exactly the same, except for the answers, you know it's an inconsistent system, automatically. And you can stop and don't have to do quite so much of the actual legwork. All right, let's look at, I already told you it's a spoiler alert, but it plays a little different because in the past, when we get to something that's always true, we just say always true. You remember that? We don't get to do that anymore with an ordered triple. What we're going to have is we're going to have algebraic expressions inside of our ordered triple. And so it looks a little different, okay? And where is my paper for that? Who knows? I might not have made one. Oh, that's fine. Here. I'm not making one. We're going to do this. So I actually really like the way I did my notes. There's your system. Do you want me to make it bigger on the wall? 3x minus 4y plus 4z equals 7. X minus y minus 2z equals 2. And 2x minus 3y plus 6z equals 5. Step 1 is always write your augmented matrix. And then realizing we need to get a 1 in that upper left-hand corner. So what is the easiest way to get a 1 in that upper left-hand corner? No, because we don't want 0. We want to get 1. And if we multiply the top row by a third, then we have a bunch of fractions. We had 3 different row operations. What was the first row operation? What did it allow us to do? Yeah, let us switch them. So what do we want to switch? Yeah, let's switch that first and second row. Let's do no math and just do some switchage. Now, theoretically, none of the other things you said are wrong, but you're going to have really gross numbers to deal with. And it takes longer. This, you're just literally flip-flopping that top and second row. And then, since we're dealing with the first column, we need to get zeros underneath that 1. How do we always go about getting zeros?
Multiply row 1 by negative 3 and add it to row 2.
Yep. And
Multiply negative 2 to row 1 and add it to row 3.
that's exactly right. Every time you're going to get a 0, you're going to have to do this third operation, where you're going to multiply a row by a constant or not. I mean, we saw in the last one we didn't actually have to multiply it by a constant at one point because we could just add them together. But either way, you're going to do that row addition situation to get your zeros. That is the only way to get your zeros. I know, you notice. But just because you notice something doesn't mean we're not going to keep going with it. I'm glad you notice. I hope other people notice. But we're going to keep going. Because like I said, this one plays a little differently. And I already told you, spoiler alert, you know what's going to happen in this one. But the formatting of how we give our answer is different with this matrix situation. Does anybody else notice anything? You notice the bottom 2 lines are exactly the same. Okay, we're going to keep playing with it though and get down to the augmented, or down to the echelon form. So how do I get that highlighted -1 to be a positive 1? Multiply that row by a -1. And then how am I going to get that 0? Yep, I'm going to add that second to that third row. And we get another, oh my goodness face. Because if I can draw an oh my goodness face in a math class, I'm going to do it. Now, when we did systems of equations, 2 equations, 2 unknowns, and we got to this point, a lot of times we just stopped. And we said, okay, it's an always true statement that told me it's our dependent system. They lay right on top of each other, and we were done. But that was when we were dealing with just 2 equations. 2 equations laid right on top of each other. with this, we're going to keep going because we can actually talk about our other variables in terms of what's left. Because all we did was we really got rid of that bottom row. By just looking at the top row and the middle row, we can write a system of equations. We can write that top row as x minus y minus 2z equals 2, and y equals a negative 10z equals 1. A negative 1, excuse me. Now, why would we want to do that? Well, think about what this system is called. It's known as a dependent system. What does it depend on? Well, what row went away entirely? Row 3, which is our z row. This whole system is dependent upon z. Whatever we plug into z is going to dictate what we get out for our x and our y. So what's going to happen is we're going to let z be z. And you're like, well, that's deep. Yeah, I know. But we're letting z be z, because if z equals z, that's always true. It doesn't matter what z is, z equals z. And I don't know why that got so bright up there on that screen. Is that better? Maybe? Is that better? Yeah. And if z equals z, we can write y in terms of z. All we did was we moved that negative 10z over to the other side. And if y equals 10z minus 1, then we can substitute that into the top equation and solve so that x is 12z plus 1. Then we know z, x, and y all in terms of z. And if we know what z is, we know what everything in this order triple is. So this is how this one looks different. Because we don't get to just stop when our row disappears and we get an always true statement. We're going to write everything in terms of z and get our ordered triple that way.